Dear students, this is Professor Manoranjan Singha, Department of Mathematics, University of North Bengal, India. Welcome to the 8th clip. I sent a message to the WhatsApp group mentioning that there is a mistake in the 7th clip, that is in the last clip. And I asked to find the mistake, considering it as a home task. Many of you replied, but except one, none of the others identified the mistake correctly. So I think I should correct the mistake first before going to discuss on some other results on locally compact topological spaces. Okay. In the 7th clip, we have proved that R omega with product topology is not locally compact, and it is okay, no doubt about it. But the mistake occurred where I claimed that R omega with box topology, R omega with box topology is locally compact. It is not correct. It is not correct. Actually, while proving this, I forgot that we were in R omega with box topology, and you know, generally we take product topology on the Cartesian product of topological spaces. Okay, we generally don't consider box topology on product, you know. That's why most probably somehow I have done this mistake. Okay, while proving this, we have taken any point x from R omega, so it will be look like xn. Okay, and I said that this product xn minus 1, xn plus 1 n equal to 1 to infinity, this is a compact neighborhood of x. I said this is a neighborhood of x, no doubt about it, because x in this product n equal to 1 to infinity, xn minus 1, xn plus 1 open, and it is totally contained in this product n equal to 1 to infinity, this xn minus 1, xn plus 1 closed. And this is a basic open set in R omega with box topology, you know. So this is a basic open set containing x, which is totally contained in this. So this is a neighborhood of x. Fine. But this is not compact. Where I have done the mistake. This is not compact. You may tell me that why not? Because every participant to this product is closed and bounded interval of R, so it is compact, and this is product of compact spaces. So by Tikhonov theorem, it is compact. But this Tikhonov theorem actually does not hold if we consider box topology. Okay. Okay, so let's prove that this is not compact in R omega with box topology. And it is not hard to prove, very easy, because okay, let me write it in this way, n equal to 1 to infinity. Okay, so x1 minus 1, x1 plus 1, this cross x2 minus 1, x2 plus 1 cross, this is countable product, so we can write in this way. Then x3 minus 1, x3 plus 1 cross dot 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 dot, dot endless. So if we consider open cover of these factors, this open cover, if we consider minus infinity to x1 plus minus infinity to x1 plus 1 and x1 minus 1 to infinity. So this is an open cover of this, you can check easily. Similarly, if we consider open cover of this, minus infinity to x2 plus 1 and then x2 minus 1 to infinity. So this is an open cover of this. Okay, similarly, now if we consider the product, if we consider product of the members of these open covers maintaining the order, okay, for example, if we consider this minus infinity to x1 plus 1 cross, now if we take this, say x2 minus 1 to infinity cross, then next will be, say, take any one of these two, so say x3 minus 1 to infinity cross dot dot, you can take minus infinity to x4 plus 1, isn't it, in this way. So this is an open set in R omega with box topology. So if we consider all possible this kind of product, okay, then they will form an open cover of this product n equal to 1 to infinity, this xn minus 1 xn plus 1. But if we drop just one member from this open cover script C, okay, then we will see that the remaining members will not sufficient to cover this. So this is an open cover of this, okay, having no finite subcover. And actually this script C contains uncountably many open sets in R omega with box topology, okay, which cover this. So this is not compact, okay. So this is the correction. So now let's start the today's discussion. Today we will characterize local compactness of Hausdorff spaces. Actually, we have already characterized local compactness of Hausdorff spaces in terms of compact neighborhood or relatively compact neighborhood in the seventh cliff, okay. Like this, if a topological space, a Hausdorff space X is locally compact if every point of it has a compact neighborhood. Another one was a Hausdorff space is locally compact if and only if every point of it has a relatively compact neighborhood. But today we will characterize a locally compact Hausdorff space in some another way, in some another useful way, okay, that will be used for the further development of the study of local compactness of topological spaces, okay. So the characterization is this, the result, let X be a Hausdorff space, X be a Hausdorff space, that is T2 space, then the following are equivalent. Following four statements are equivalent. Statement A is X is locally compact. X is locally compact. Statement B is for each point X of capital X and each neighborhood U of X, there is a relatively compact open set V such that X belongs to V. V, of course, subset of V bar, totally contained in U. Okay. C. Statement C is for each compact set C and open set U containing C, there exists a relatively compact set V such that the C subset of V subset of V bar, which is totally contained in U. And the statement D is the space X has a basis. The topology on this underlying space X has a basis beta consisting of relatively compact open sets. Okay, we will prove that these four statements A, B, C, D are equivalent. Okay, actually we will show that is A implies B, then B implies C, then C implies D, and then D implies A. Then if any one of them is true, then other three will be also true. Okay, let me explain this. X is locally compact, nothing to explain more. Statement B says that if this is the space X and if small x is any point of it and this U any neighborhood of it, then there exists a relatively compact open set V. Okay, relatively compact open set V containing this X, okay. So there exists a relatively compact open set V whose closure also contained in U. So this closure of V also contained in this U, and closure of V is compact because V is relatively compact by definition. Okay, and statement C is same, just the point X is replaced by any compact set C. So any compact set C and any open set U containing this C, we should have an open set V which is relatively compact. Okay, or it relatively compact open set. Okay, it must be open. So relatively compact open set V such that C is totally contained in V, like this. Here point is contained in V and V bar also contained in U. Okay, so B, C similar. Okay, here in the statement C, the point small x in the statement B is replaced by a compact set C. Actually, in a Hausdorff space, compact sets behaves like points. Okay, so we will prove now this equivalence of these four statements. Fine. So let me sketch the proof. Okay, this is the result. First we will prove that A implies B. Okay, so proof, sketch of the proof. A implies B. That is, we are assuming that the space is locally compact. Okay, we will prove the statement B. Fine. Okay, so since X is locally compact, so for this X in the statement, for this X in capital X, there exists some relatively compact neighborhood N of X. X is Hausdorff, so it is locally compact. So for every point of it has a relatively compact neighborhood. Okay, fine. So let N be a relatively compact neighborhood of this point X. Now by the definition of neighborhood, so there exists an open set W. So this is open set in X. Okay, open set W such that this X belongs to W and W totally contained in N, and this implies that X belongs to W subset of W bar. So W bar subset of N bar, W bar subset of N bar, and this N bar equal to N. Why? Since the underlying space is Hausdorff and N is compact. N is compact neighborhood, so N is compact. Therefore, N is closed. Compact subset of a Hausdorff space is closed. So N is closed. So N is closed, so N bar equal to N. Fine. Find it, this N is compact. Okay. So this W bar being a closed subset of a compact set, so W bar is compact. And the W bar contains an open set containing X. So W bar is a compact neighborhood of X. Okay. or W is a relatively compact neighborhood of X. Okay, in X, everything we are in X. So this implies this W is a relatively compact neighborhood of X in X. This is important. In X. Also, this W bar that I said, W bar is closed subset of a compact set. So this is compact. So W bar is compact, as well as this is a subset of X, and X is Hausdorff. Hausdorff property is hereditary, so W bar is Hausdorff. So W bar is compact as well as Hausdorff, and hence W bar is T4, that is T3, so regular. Hence this is regular. I will use regularity of this W bar. Okay, the main space is Hausdorff, but this W bar is regular. Okay, stronger than this. So W bar enjoys stronger property than the underlying space, and I will use this strength of this W bar, and that's why for the time being we'll confine ourselves within this W bar. Okay, so this is W bar. The main space is X. We will confine for the time being within W bar because it is stronger than this X. I will use this strength of W bar. Fine. Now, in the statement, this is neighborhood U of X. Okay, so U is a neighborhood of X. Of course, in X. Now, U being a neighborhood of X in the main space X, then W bar intersection U, this is a neighborhood of X in W bar, isn't it? So this is a neighborhood of X in W bar. We know open set in X intersection W bar is open in W bar. Closed set in X intersection W bar, closed in W bar. The same way. This U intersection W bar, U is a neighborhood of X. So this is a neighborhood of X in W bar. Okay. So if U is like this, X is here, so U is like this, then we are considering this. This is W bar intersection U. Okay, this is also neighborhood of X but in W bar. Okay, so W bar is regular, and this is a neighborhood of X. So by necessary and sufficient condition for a topological space to be regular, there exists an open set in W bar whose closure in W bar totally contained in this. Okay, so by regularity of W bar, there exists an open set G in W bar such that X in G subset of closure of G in W bar subset of this neighborhood, that is W bar intersection U. This W bar intersection U. Okay. Fine. Okay. Now G open in W bar. So open in W bar. So open in W bar means this is an intersection of an open set in X with this W bar. So let G equal to E intersection W bar, where E is an open set in X. This is open set in X intersection W bar. That's why this is open in W bar. That is G. Okay. Okay. Now we will define the desired relatively compact open set V by the help of this E. Okay. Now let V equal to E intersection W. W means this W. This W. Okay. W is relatively compact neighborhood of X, and it is open also. Okay, so W is relatively compact open neighborhood of X in X. Okay. So W is open in X, E is also open in X, so V is open in X. Okay. And E contains X because X in G, so X in E. X in E, and W is a neighborhood of X, so X in W also, so X in V. So V is an open set in X containing X. Okay, then V is an open set in X such that this X belongs to V. Fine. Now this V bar will show this is relatively compact, this V. That's why we have to calculate V bar. The V bar is, V means this, so E intersection W bar, and this is a subset of E bar intersection W bar. Closure commutes with finite union, but this is intersection. In case of intersection, okay, if closure is distributed over the participant to the intersection, then it becomes larger. Okay. Okay. And G is E intersection W bar. So closure of G in W bar, it will be this closure of G in W bar. Okay, closure of G in W bar will be closure of G in X intersection W bar. Okay, so we will get ultimately E bar intersection W bar. You can check easily. So this is nothing but E bar intersection W bar. Okay, and we already got this closure of G in W bar subset of this W bar intersection U. So this is subset of W bar intersection U. Fine. Okay. Oh, light gone. Okay. Okay. Fine. So we are done almost. Why? Because this is a subset of W bar, and W bar is compact. This W bar is compact. So V bar being a closed subset of a compact set is compact. So this implies V bar is compact. V bar is compact. Not only that, and this V bar subset of this, we can write this is also a subset of U also. So V bar contained in U. So accumulating all those things, we see that this V is an open set. V bar is compact, so V is locally compact. So V becomes a relatively compact open set. Okay. So V is a relatively compact open set in X such that this X belongs to V, X belongs to V, and V of course subset of V bar, and this V bar totally contained in U. Okay, and this is actually B, which is the statement B. So statement B follows from statement A. Right. What is the statement? Oh. This is the statement. This statement B. For each point X and each neighborhood U, there exists a relatively compact open set V such that this. Okay, so we are getting a relatively compact open set V in X such that this. So B is achieved. So A implies B, we have done. Now we will prove B implies C. It is very easy. Okay, now we will prove B implies C. Statement B implies statement C. This is the. Okay, now let me prove this. B implies C. Okay. For every point small c of capital C which is totally contained in U, okay, by B, just look at this C to this, okay, this and this. So U is a neighborhood of C. U is an open set containing C, so U is a neighborhood of C, isn't it? Now by B, U is a neighborhood of here C is playing the role of X in the statement B. Okay, so there exists, for every this there exists a relatively compact open set, say BC. Okay, BC such that X belongs to BC, and this BC subset of course BC bar subset of U. This is by using B. Okay, for every C in capital C, we will get this open set VC, relatively compact open set VC, such that this. Now, if we collect all those open sets VC, okay, then it will cover this C, because for every point we are getting an open set containing it. Okay, so all the points of C will be covered by all those VC. Okay, so then this script C equal to collection of all those VC, C in capital C, this forms an open cover of C. Now C is compact given that C is compact. Since C is compact, so there exist finitely many members in script C, say BC1, BC2 BCK in this script C, such that this B equal to their union BCI, I equal to 1 to K, that will contain the compact set C, that will cover C. Okay, fine. Since every VC is open, so every VCI open, so the union, that is V, is open set containing C. Okay, this implies V is an open set, okay, and B contains C. Now we will show that this V is relatively compact and V bar is contained in U. Okay, V bar is contained in U and relatively compact. B is open set, done already. Okay, so we have to show two things more. B is relatively compact and V bar subset of U. A V bar subset of U, very easy. Now V bar equal to, V is this, so V bar equal to this union I equal to 1 to K VCI whole bar. Okay, fine, and this equal to union I equal to 1 to K VCI bar. Every VC is relatively compact, so their closure is compact. So VCI, they are compact. So this is finite union of compact sets. So this is finite union of compact subsets of a Hausdorff space. So it is again compact. So V bar, this being a finite union of compact sets in a Hausdorff space, X is compact. Okay, so V bar is compact, that is V is relatively compact. So B is a relatively compact open set containing C. So we got this, we got an open set which is relatively compact, and we have proved this portion, C containing B, just we have to show V bar subset of U. It is also very easy. Okay, now every VC bar contained in U, so every VCI bar contained in U, so their union will be also contained in U. So V bar is contained in U. Okay, also since each VCI bar contained in U I equal to 1 to K, B bar also contained in U. Okay, so hence B is a relatively compact open set in X such that X belongs to V analysis, such that C subset of V and V subset of V bar, of course, and V bar subset of U, which is C. So B implies C also done. Now C implies D. It is very easy. C implies D. Okay, what is this? Okay, so assuming should write in this way, no? This way. Fine. Assuming that C is correct, we have to prove the truth of D. Okay, so assuming that this for each compact set C and each open set U containing C, there exists a relatively compact open set V such that this, we have to show that AX has a basis beta consisting of relatively compact open sets. Okay, so let beta be the collection of all relatively compact open sets in X. This beta is actually non-empty. Why? Since X is housed of and locally compact, so every point of X has a relatively compact neighborhood. Okay, so every point of X has a relatively compact neighborhood. So this is relatively compact. What does it mean? N is a neighborhood and n bar is compact, isn't it? The neighborhood means there is an open set, so O, containing X contained in N. So if we consider the closure, so O bar subset of N bar. Now N bar is compact and O bar is closed. So closed subset of a compact space is compact. So this O bar is compact, so O is relatively compact and O is an open set containing X, so it is also a neighborhood of X. Okay, so this O actually a relatively compact because O bar is compact, relatively compact open, who is open set in X containing small x. Okay, so we see that since X is housed of and locally compact, there are relatively compact open sets. So this beta is non-empty. Since X is housed of and locally compact, okay, this beta is non-empty. Fine. Okay, now we have to show that this beta is a basis for the topology on X, and for this we have to take any open set in X and we have to show that it can be written as a union of members of beta. So let U be any open set, U be any open set in X. Okay, and let small x in U. Okay, so U is a neighborhood of X. Fine. U is an open set X. Now we have to show C implies D. Somehow we have to use the statement C, and it involves compact set C contained in an open set U. Here X contained in this U. So somehow we have to make an arrangement so that we can use C and we can obtain D. Okay, so let me rewrite this thing in some way so that we can use C. Since X in U, we can write this singleton X subset of U. Okay, and singleton X is compact. Any finite subset is compact in any topological space. Okay, then this and this singleton X is compact. This is compact. So we can use C, and using C, using the statement C, okay, there exists a relatively compact open set, say Vx, such that X belongs to Vx. Singleton X subset of Vx means X belongs to Vx, and Vx subset of Vx bar, and this Vx bar subset of this U. Fine. Now U can be written as union of this singleton X. Okay, just we are taking X from U and collecting again, so we'll get U again. So this singleton X subset of X in Vx, so singleton X subset of Vx. So if we replace this singleton X by Vx, we will get larger thing, so X in U. Now every Vx contained in U, so this union also contained in U, and this implies U subset of this, and this is subset of U, so U equal to this union Vx X in U. Okay, so Bx, this is relatively compact open set, and beta, collection of all relatively compact open set. So Bx is a member of beta. So these, all those Vx are members of beta. Okay, since this Vx in beta for all X in U, isn't it? So U is a union of members of this beta, and U is arbitrary open set. We have taken any open set in X. Okay, so this beta is a basis consisting of relatively compact open sets. So we are done. Okay, so this is C implies D. Okay, done. Now D implies A. It is very easy. D implies A. Fine. What is D? D says that It is actually trivial. So D implies A. D says that X has a basis beta consisting of relatively compact open sets. Okay. And we have to show that X is locally compact. Okay. So let small x in capital X. Then by the definition of basis, there exists a member, say B in beta, such that this X belongs to B, the first condition to be a basis. Okay. Now B in beta. Beta means this, consisting of relatively compact open sets. So this B is a relatively compact open sets. So X in B, which is relatively compact open set. So for every point X of capital X, we are getting a relatively compact open set containing X. Okay, open set containing X, so B is a neighborhood, so I may write it's a relatively compact neighborhood of X. Okay, so every point of X has a relatively compact neighborhood. Okay, also X is Hausdorff, given X is Hausdorff, X is Hausdorff. Okay, also X is Hausdorff. So X is locally compact. Okay, which is A. Statement A. So we have proved A implies B, B implies C, C implies D, and D implies A. Okay. So we have proved this result. Fine. Okay. We'll continue the study of local compactness or topological spaces. Okay. So for the time being, I stop here. Okay, keep watching. Okay, thank you.